So having understood the procedure, let us solve one problem. The problem will clarify lots of doubts which are there in our mind, and it will be making the process of understanding smoother. So there is a problem which has been given to us. The problem goes this way. Design a rectangular beam to carry UDL of 35 kilonewton per meter under working condition. So the service condition or the working condition has been given, and it has been told that this load does not consider the self weight. So normal working condition load is 35 kilonewton per meter and the self weight is not considered. The beam is a simply supported beam. It has an effective span which has been already calculated and given to us as 4.5 meters. The grade of concrete and steel are also provided to us, so that is M25 concrete and Fe415 steel. Now when do we get a condition like this? Say a designer is actually designing a beam. He has already decided that the type of concrete is going to be M25. Maybe he has also designed some of the items. So M25 concrete and Fe415 steel is already decided. He has already calculated the effective span, and he has told us the effective span is this much. That parameter has been given, so that parameter cannot change. So having been given this, they want us to design. So let us see what all things have not been given, what all things we are needed to find out or design in this particular problem. In data, what we have been given is W dash, that is the load which is coming over the beam other than the self weight, that is 35 kilonewton per meter. It's a simply supported span with effective span of 4.5 meters, M25 concrete, Fe415 steel, and what we need to find out: the width, effective depth, the overall depth, the amount of steel, that is the diameter, and the number of bars. Solution. So when we are going for the solution, in the calculations we have step number 1, grade of concrete, that is already given, grade of steel is already given. Now we look at step number 2. In step number 2, assume the beam width as 230 mm. So we start by assuming the width as 230 mm. Maybe another engineer will assume it as say 250 mm, someone else may assume it as 200 mm, whatever. So assuming the beam width as 230 mm. So in this problem we are taking the width as 230 mm. We are taking the depth to the breadth ratio as 2. Now having given as 2, d will be d upon 230 will be equal to 2, or d will be 2 into 230. So the effective depth comes equal to 460 mm. Please note, we are trying to arrive at the value of effective depth and the width. These are still the initial stages. This is not the final effective depth. These may be changing. This may be different. So now that we have got 460 mm, round off the value obtained to about 50 mm on the higher side. So from here, somewhere plus 50 mm we will be doing to 460 to come to a effective depth. So 460 we have got. So consider cover as 50 mm for durability. That is, if we look at the code from durability condition, for moderate condition it is 35 mm, and fire resistance for 2 hours as 40 mm. So 50 is quite huge. So in between 35 and 40, if we assume, we can take cover as 40 mm. I think 40 is enough, and assume bar diameter as 16 mm. So considering all this, we can take in between. So first we thought that we could take 50 mm for durability. In moderate condition it says it should be 35 mm, so we are taking 35 mm, and fire resistance of 2 hours is 40 mm. So in between 35 and 40 we would be choosing 40 mm. So 460 is the value of D which we have got. About 50 we were supposed to increase, so I have increased by 42. It can be anywhere in between 40 and 50, so somewhere around 42. And then this is 40, the cover which we have taken from here, and this is 16 by 2, the diameter divided by 2. See, this has been taken as 42 only to round it off, so that capital D becomes equal to 550. Suppose I had taken this as 40, then this would have become 548. For the calculations, all the calculations, this becomes easier, a rounded value becomes easier. So if the overall depth is 550, what becomes, how much would be my effective depth? My effective depth would be approximately equal to the overall depth minus clear cover minus half the diameter. So that would be 550 minus diameter divided by 2 would be somewhere around 16 by 2 minus clear cover is 40. We are assuming clear cover is 40. So D comes 502. So say I take it as 500, there is no problem. I have taken it as 500. If you have observed, we had got it as 460. We are taking D as 500. So that is 40 mm more than whatever. Please note, this is still the assumption. We have assumed the small d to be 500, the capital D to be 550, and the B, the width, as 230. Now we are going to the next step. In the next step, find the bending moment acting on the beam due to all the loads, that is including the self weight of the beam. Now calculate the value of BMU by applying partial load factors. Now over here, self weight of the beam would be B into overall depth into 25. So it is 0.23 into 0.55 into 25. Self weight of the beam comes to equal to, when we solve this, 3.163 kilonewton per meter. Therefore the total UDL per meter span would be that W dash, the load which is coming on the beam, plus its own self weight, that is 35 plus 3.163, so that comes to 38.163. I round it off on the higher side for my calculations. It becomes easier in calculating. So this I round it off as 38.5 kilonewton per meter. So the total load coming on the beam per meter span, per meter of the span, is the load which is on the beam plus its own self weight. So that is 35 plus 3.163. So we have rounded it off from 38.163 to 38.5. Having got the value of W, let us proceed further. Bending moment we know for a simply supported beam with UDL is WL squared by 8. Please note over here the loading which is given is a UDL plus the self weight also is UDL. So the total load is UDL per meter span. So bending moment is given by WL squared by 8. W is 38.5. L, the effective span, is given to be 4.5. So 4.5 square by 8. So bending moment comes equal to 97.45 kilonewton meter. Having got the bending moment coming on the beam, now we have to find the ultimate bending moment due to the partial load factor, how much it is. Now partial load factor as far as dead load and live load are concerned is 1.5, which we have seen in the previous chapter. So BMU will be equal to 1.5 into the bending moment. So 1.5 into 97.45. So BMU is equal to 146.18 kilonewton meter. That means the ultimate bending moment acting on this beam is 146.18 kilonewton meter. Now we have already assumed the beam having the width as 230 mm, the overall depth as 550 mm, the effective depth as 500 mm, the type of steel and concrete, steel is Fe415, concrete is M20. So having assumed this, let us find out what is its own capacity of resisting maximum bending moment. In the balance case, maximum bending moment. So knowing how much maximum bending moment it can take, if that moment is more than or equal to this bending moment which is coming on the beam, we know that this section, whatever has been assumed by us, is acceptable. So we are going to step number 4. In step number 4, calculate the MU limiting of the beam, that is use IS 456 clause G1.1c page 96 to get the value of MU limiting. Now for Fe415, XU max by D is known to be 0.48. This we have already seen from page number 70 of the code, that is clause 38.1. We have seen from there that XU max by D is 0.48. So having got this formula, MU limiting we are trying to find out 0.36, XU max by D is 0.48. So 1 minus 0.42, this is 0.48, B is 230, D is 500, so 500 square into FCK is 25. Having got this done, MU limiting comes to 198.32 into 10 raised to 6 Newton mm. How much is the maximum bending moment, ultimate bending moment coming on the beam? That is equal to 146.18. And how much is its capacity? Ultimate capacity 198.32 into 10 raised to 6. So we know that the capability capability of the beam is 198, but the bending moment coming is only 146.18. Since mu limiting 198.32 is greater than the bending moment ultimate coming over the beam, that is 146.18, that means the assumed section, the assumed sectional data, the width, the depths, that is the effective depth, overall depth, the grade of concrete, grade of steel, everything, all these parameters are acceptable. Step 6. Since mu limiting is greater than bending moment ultimate, obviously the design is a under reinforced section. If you remember, for a balance section, mu limiting is equal to the bending moment coming from outside, and for a under reinforced section, the mu limiting is always greater than the bending moment which is coming from outside. So in this case we have mu limiting greater than the bending moment, the ultimate coming from outside, so the design is an under reinforced section. If it is an under reinforced section, go to step number 7, find the value of AST. Use G1.1b on page 96 to get the value of AST. In this formula, mu will be replaced by the external acting bending moment. So having done that, write mu as external acting bending moment. This is 0.87, Fy is 415, AST is the one which we are trying to find out. D is already known, is already calculated by us as 500. So 1 minus AST is to be found out. Fy is known, that is 415, B is 230, D is 500, and FCK is 25. Having known all these parameters which we have written down over here, mu is 146.18 into 10 raised to 6. Please note this has to be in Newton mm because all the values are in Newton and mm. Fy is 415, AST we are trying to find out, D is 500. Similarly over here, B is 230, D is 500, FCK is 25, Fy is 415. Solving this, we get the value of AST is equal to 936.29. Obviously this becomes a quadratic equation because the variable is appearing at two different places and it gets multiplied. So solving the quadratic equation, we get the value of AST as 936.29 mm square. Now going to the next step. The next step is calculate AST minimum in tension for a beam. A beam in bending has to have a minimum amount of steel in tension. How much is it? Now the code says in clause 26.5.1, AS upon BD is equal to 0.85 upon Fy, AS upon BD is equal to 0.85 upon Fy. So AS cross multiplying this has given me 0.85 into BD upon Fy. So AS is equal to 0.85, B is 230, D is 500, Fy is 415. So we get the value of AS as 235.54 mm square. Now this value is much lesser than 936 which we have got over here. We had got 936, this is 235. So what we are going to provide is much more than the minimum. So whichever is more, either the one calculated or the one from minimum, whichever is greater, that much amount we have to provide. So now the next step, step number 9, we have decided that we are going to provide 936.29 mm square of steel, area of 1 bar of 20 mm. We are choosing 20 mm. Please note earlier we had chosen 16 only to decide about the effective depth, but now we are choosing 20 mm bar. As I have said, we have the freedom of changing. If we need, we can use 16 mm bar also, there is absolutely no problem, but I have changed it. I want 20 mm bar over here. So area of 1 bar comes to 314 mm square. What will be the number of bars? Number of bars will be total area divided by area of 1 bar, total area of steel required divided by area of 1 bar. So number of bars will be 936.29 divided by 314, or number of bars will be 2.98. So that means rounded off on the higher side is 3. So provide 3 bars of 20 mm diameter. Having done that, step number 10 is give the detail of the section graphically. That's the beam, that's the effective span which has been given to us. The width has come to 230, the overall depth is 550, the effective depth is 500. There are 3 bars of 20 in tension. They run from one support to the other support, and there are bars provided on top. These are 2 bars of 8. Please remember, these are dummy bars called as the hanger bars. The purpose of these hanger bars we will be coming to subsequently. So the beam in elevation, in sectional elevation, looks like this. The main reinforcement goes inside the support over here, goes inside the support over here. 3 bars of 20, only 2 hanger bars have been put over here. If I take a section, sectional details appear like this. So having solved this problem, we have gone through all the 10 steps, and finally we have drawn the sketch. This is the way we draw the sketch.